Hello, Algebra 2. I'm sorry I'm not in class right now, but I am not feeling well, so hopefully this video lesson will help you learn this and you can stay on track with all the other classes. So if you have any questions, please feel free to email me, but please watch this video lesson, follow along. It's not a hard lesson, and I do want to stay on track, so I expect you guys to learn this from this video. So to begin with, this is lesson, I believe, 5-3 now. We've done factoring day 1. This is technically factoring day 2, completing the square. In order to complete the square, which if you've never heard of that from Algebra 1, this is another technique for solving quadratics. You have to first recognize what a perfect square trinomial looks like. So perfect square trinomials, you would have seen this on your Algebra 1 star chart, have the formula m plus n, the whole thing squared. So this is our repeated root. If you remember, if I have a quadratic that's sitting right on the x-axis and its vertex is touching the x-axis, then its solution, there's only one because it only hits the x-axis once. So we give it a repeated root where it's something plus something, a factor, times something plus something exactly the same. So we write it as the factor squared. So when that happens, it's very useful that we can recognize it as a perfect square trinomial. So first, the parts that I need to recognize from the formula is that it is some value plus some value, and the entire factor, the entire binomial, happens twice. And if I FOIL that out, I should get m squared plus 2mn plus n squared. Now, there's two formulas, a positive version and a negative version. So we have m squared minus 2mn plus n squared. If this scenario happens with our trinomial, we write minus on the inside. In practice, x squared plus 10x plus 25 is a perfect square trinomial. So it's of the form where it's a perfect square in front and a perfect square in the back. And I write the root of those, m and n. So if m squared is x squared, then I write an x. If n squared is 25, I write a 5. And then I look at the sign, in this case, plus 2mn, the middle term, so I should write a plus in the middle of my factor binomial. Similarly, with 9x squared plus 6x plus 1, 9x squared would be written as 3x. 1, the perfect square, is written as 1, and in the middle I check the sign, so I write a plus. This is 3x plus 1 times another 3x plus 1. When FOILed together, will give us 9x squared plus 6x plus 1. 4x squared minus 12xy plus 9y squared. My perfect square in the front is 2x. And then the perfect square in the back, 9y squared, becomes 3y. And I check the sign. This is the first case where I have a minus middle term. So the formula tells me if the middle term is being subtracted, I write a minus on the inside. So real fast, if you're curious what these look like when they're FOILed together, if I take the first one, the easiest, x plus 5, the whole thing squared, it really is a perfect square trinomial of this form, because if I write x plus 5 times x plus 5 and multiply them together, using FOIL, I get x times x is x squared. 5x plus another 5x is our 10x, and 5 times 5 is the 25. So if as long as it's in the form of a perfect square trinomial, and I'll shorten that to PST, as long as it's a PST, a perfect square trinomial, then I can write it in its binomial squared form, which is super useful for factoring when you just want to square root something. So, how can you quickly tell if something is a perfect square trinomial? If you get a trinomial, you start with this checklist. Are the first and the last terms perfect squares? So we see in all of these examples that's true. So let's pick one and say x squared plus 10x plus 5, and go through the process of how I would quickly look at this and check if it is a perfect square trinomial. The first and last terms are definitely perfect squares, so check. Then, looking at b, the middle term, 10, have it, then square it. So b divided by 2, and then you square that. Check does that value equal the product of a and c? So in this case, my a value is 1, because it's 1x squared. So a times c would just be 25. So I'm checking, is my b value 10? When I have it and square it, does it really equal 25? Well, 10 divided by 2 is 5. The whole thing squared is indeed 25. So if all of those things are true, this must be a perfect square trinomial, and I can immediately write it in its binomial squared form. So some practice. Which of these are perfect squares? To begin with, the whole point of perfect squares are checking if I can square root it. So x squared is a perfect square, clearly, because I can square root it easily. It's good to go. It's x. Or x times x, pardon me. X squared minus 18x plus 81. So I check, is the first term and the last term perfect squares? X squared is a perfect square, 81 is a perfect square. So that is x and 9. And then I check the middle term, negative 18, the b value. Is it, when divided by 2, when I have it, then square it, does it equal either a or c? Because in this case, a times c, the product, is just 1 times 81, or 81. So negative 18 divided by 2 is negative 9. Negative 9 squared is indeed 81. This is a perfect square. This whole trinomial is a perfect square of the form the root of the first term, so x, the root of the last term, 9, and then I check the sign. The middle term is being subtracted, so I write a minus, and this factor will happen twice, so it is indeed a perfect square. X squared minus 4. This is a difference of 2 squares, so that's going to become x plus 2, x minus 2. Since these are two different factors, I can't write this of a factor squared. They're not the same. So this is no, not a perfect square. So this one is yes, this one is yes, and the difference of 2 squares is not in itself entirely a perfect square. It's made up of perfect squares, but it is not itself a perfect square. X squared plus 12x plus 12. X squared is a perfect square. 12 is not. I can immediately stop here. This is not a perfect square. Looking at it, it's not even factorable either. The last one. I check the first term. 36x squared is a perfect square. That's 6x. 4 squared. 4 is a perfect square. That's 2 squared. And the middle term, negative 24. If I have it, and then square it, does it equal a times c? Well, a times c in this case is 36 times 4. So that's going to be some massive value. So let's take a look at what that could be. That is 36 times 4 is going to be 4 times 6 is 24. 3 times 4 is 12, plus 2 is 14. So 144. So then I check, is my middle term negative 24 divided by 2? That'd give me negative 12. Negative 12 squared is indeed 144. Check, this is a perfect square. So it can be written as the perfect square trinomial in binomial form. 6x, then 2. Look at the sign of the middle term, so I write minus, and this happens twice. So 6x minus 2, the whole thing squared. So yes, this is a perfect square trinomial. Check the b value, have it, and square it. Does it equal a times c? So we use perfect square trinomials for this method, completing the square, which is simply finding the missing value that makes a quadratic a perfect square trinomial. So why would that be useful? I can make any quadratic, a perfect square trinomial. Why is that useful? Because then it gives me a perfect example that I can use square root property of and just immediately square root both sides. So what am I looking for is, if I have any quadratic of the form ax squared plus bx, and I'm missing some part of it, I'm going to complete the square algebraically by beginning with, if at all possible, it makes your life easier if you divide by a to make the leading coefficient 1. Much, much simpler if we do that. So divide or factor out this GCF of a and divide everything by a. So this part is missing. We don't know what that value is yet, so I can't divide it by a yet. This thing doesn't even exist. So now I'm going to have x squared plus b over ax, and we're going to add something to this to make it a perfect square trinomial. Well, if you recall, we always want to check, is my middle term, when I have it and then square it, does it equal the front or the back, or a times c? Well, in this case, if I make a 1, that simplifies things. That's the whole point of dividing by a. So I want to make sure my last term, whatever it is that I'm adding to this quadratic, is the middle term halved and squared. Well, my middle term when I divide everything by a is b over a. So I'm taking b over a, halving it, so dividing by 2, so tack on a 2 in the denominator, and then squaring the whole thing. If I add this to my perfect square trinomial, or sorry, not my perfect square trinomial yet, but if I add this to any quadratic of this form, it inherently becomes a perfect square trinomial. So this is a perfect square in the back, a perfect square in the front, and my middle term does in fact equal itself divided by 2 and then squared. It's going to equal our 1 times c value. So we usually take this whole thing and convert it to its binomial squared form. So that's going to look like something squared. So in this case, the first term, x squared, that's going to be written as x. The last term, b divided by 2a squared, well, we know its root. It's b over 2a. We add it, and then there's our perfect square trinomial, ready to be square rooted whenever needed. So that's pretty abstract, but in essence, we need to know if you add b over 2a squared to any perfect square trinomial, you're good. And if you divide everything by a, if there is a coefficient a, then it makes your life easier because then we work with an a that's just 1. So a good example of this would be 2x squared plus 8x. This is not a perfect square trinomial right now. I want to add something to it. Well, the first thing I want to do is divide everything by its leading coefficient a. If I do that, it simplifies things, and I only have to focus, does my middle term add to c? So I have divided by 2, I'm left with x squared plus 4x. Now I have a new a. A is 1, and b is 4. So that's b, this is a. What I want to add to this thing is I take the middle term, 4, halve it, and square it, and whatever I add to this thing will inherently make it a perfect square trinomial. So that is going to be 4 divided by 2 is 2, 2 squared is 4. So this is a perfect square trinomial, so I could write this of the form x, and so the root of the first term, and the root of the last term is 2, square root of 4 is 2. It's plus, so I write a plus, and this is x plus 2, the whole thing squared. Now, prove it. If I really wanted to check and double see, I should FOIL. X plus 2 times x plus 2 is in fact x squared, plus 2x is plus 4x, and 2 times 2 is 4. So this was indeed, adding 4 makes this a perfect square trinomial. So a cool visual representation on the next page. What's really happening when I say completing the square? Geometrically, we are literally completing a square. So imagine I'm giving you something x squared plus bx. So I don't have an a here. Let's just ignore it for now and pretend my leading coefficient's already 1. So I don't have to worry about it. You take your middle term and say b times x is a rectangle made out of side length b times side length x. And x squared, like the name suggests, is a square of area x squared with side length x and x. So notice the square has side length x. This rectangle also has side length x, so they fit. But the rectangle has one side length b, because b times x is bx, length times width. Length times width. So what are we doing when we complete the square? We want to add b over 2 and then square it. Well, where's the b over 2 coming from in geometric form? You take bx, that rectangle, and cut it in half. So this side length b becomes b over 2 and b over 2, but it still has a length of x. So what do I do with these two puzzle pieces? I take them, drag them onto the sides where they fit. So if I have a side length x, and this is also side length x, then they fit like puzzle pieces on the side. These are equal lengths. So the length of the square and the length of this rectangle is still x on both cases. And then we have an almost square with one missing piece. A tiny little square that we must complete. Now, what is the side lengths of this tiny square? Well, if the rectangle is made out of length x and width b over 2, and width b over 2, then this rectangle is side length b over 2 times b over 2, or it has an area of b over 2 squared. So we are literally completing the square geometrically when we complete the square algebraically. So both are good representations and understanding of what happened. So a quick review. Square root property. We use this when it's much easier than factoring. So in this case, x squared minus 4 is a difference of two squares. I could go through the zero product property and do every step, but if I add 4 to both sides, so not set equal to 0, isolate the thing that is squared. So the thing that is squared is all by itself. Whenever that happens, we're allowed to just square root it. And we're left with x equals plus or minus square root of 4 is 2. Square root property can be much faster than factoring when it's possible. Now, square root property is going to work on x squared plus 8x plus 16 because this is a perfect square trinomial. Now again, how do I check? The first term is a perfect square. The last term is a perfect square. Take the middle term, have it, and square it, and we see 8 divided by 2 is 4. 4 squared is 16. This equals a times c, which is 1 times 16. It is a perfect square, so I can immediately write it as a binomial squared, which is x squared becomes x, 16 becomes 4, the sign is plus, so I write a plus, this equals 1. This is something that is squared, and it's all by itself. I can square root both sides, and I get x plus 4 equals plus or minus, and the square root of 1 is 1. Solving for x, I subtract 4 from both sides, and we get x equals negative 4 plus 1, and negative 4 minus 1. And this becomes two separate things. Negative 4 plus or minus 1 is two values. X equals negative 4 plus 1 is negative 3. Negative 4 minus 1 is negative 5. So those are our two roots. So that's a review of square root property. Why do we want to get perfect square trinomials? So that we can do this. So, some helpful review. How do we complete the square? I'm given x squared minus 2x, and I want to know what's the c value that completes the square. What's the c value that makes this a perfect square trinomial? Well, if a is already equal to 1, then don't worry about it. We don't have to divide it through. We just take the middle term, negative 2, and have it, then square it. That's going to be negative 2 divided by 2 is negative 1. Negative 1 squared is positive 1. So what's the c value that's going to make this a perfect square trinomial? If c is 1, then x squared minus 2x plus 1 can be written as x minus 1, the whole thing squared. A perfect square trinomial. All right? X squared plus 5 over 6x plus c. Take the middle term, because a is still equal to 1. I don't have to divide everything. Take the middle term, 5 over 6. Have it, and then square it. So 5 halves divided by 2 is just 5 fourths divided by 5 fourths, and then we square that. And if I square 5/4, it goes to the top and the bottom. So this is 25/16. So what is the number squared that will give us a perfect square trinomial? If I have x squared plus 5/6 x plus 25/16. If I do this, this is a perfect square trinomial. An ugly one because of all the fractions, but this can be written as x and then 25/16. The root of it, we already saw it, it's 5/4. So we write x and a 5/4. The sign is plus, so we say plus the whole thing squared. This is now a perfect square trinomial. Now, how do we use this to solve? Well, suppose I have x squared plus 16x minus 7. My method one is, can I factor this? So, two numbers that multiply to -7 but add to 16. No, not possible. Especially because 7 is prime. Go on to square root method. I can't square root this whole thing because there's too many x's. This wouldn't be pretty, and I can't isolate this x squared and have this x still be here. So instead I check, can I turn this into a perfect square trinomial? Add 7 to the other side. We don't need the 7 right now. It did not help us factor, so get it out of the way. X squared plus 16x equals 7, and I'm going to add something to both sides of this equation. Because if you add it to one side, you have to add it to the other. So we need to know what's the last term that makes this a perfect square trinomial. It's the middle term halved and squared. So 16, halve it and square it, is 8 squared, or 64. So if we add 64 to one side, we must add it to the other, and we get a perfect square trinomial, which is x, and then 64 becomes an 8. We write it squared, and this equals 64 plus 7 is 71. Square root both sides. So this is truly ugly and horrid. Square root is 71, nothing pretty. So x plus 8, the whole thing squared, now becomes x plus 8 equals plus or minus the square root of 71. Square root of 71, that's as absurd as it gets, mostly because 71 is a prime number, so it's only made up of 7 times 1. So there's no, 71 times 1. So there's no way I could pull something out of this and get something nice. So we have, subtract 8 from both sides, x equals -8 plus or minus root 21. Those are our two roots. -8 plus rad 71 and -8 minus rad 71. So, a harder example, a is not equal to 1. If possible, divide everything by our a value so that we can have a equal to 1. Makes your life easier. 2 divided by 2 is 1. 8 divided by 2 is 4. -3 over 2 is just -3 over 2. And 0 divided by 2 is still 0. So we have 4x and x squared. This is not a perfect square trinomial. I'm not even going to try to see if this is factorable. Instead, move this -3 halves out of the way. And we have x squared plus 4x, and we're going to add something to this. We don't know what it is yet. Equals, add 3 halves to both sides. We have 3 halves on this side, plus something. So, we take the middle term, halve it and square it. That's 4 divided by 2 squared, or 2 squared. Add 4 to both sides. And we have a perfect square trinomial, x plus 2, the whole thing squared, equals 3 halves plus 4. Well, 4 written as a half is 8 halves. And 3 plus 8 halves is 11 halves. Square root both sides. And we have x plus 2 equals rad 11 over rad 2. And then plus or minus. Subtract 2 from both sides. And we get negative 2 plus or minus radical 11 over radical 2. Oh, and real quickly before I forget, we should take this radical 2 and rationalize the denominator. In other words, we should not leave a radical 2 in the denominator. So I'm going to write rad 11 over rad 2 as, well, if I multiply it by 1, nothing breaks. And rad 2 over rad 2 is 1. And so this becomes rad 2 times rad 2 is rad 2 squared, or just 2 in the denominator. And square root of 11 times square root of 2 is going to give us our square root of 22. So this is really negative 2 plus or minus rad 22 over 2. And that would be our final set of 2 roots.